Hello, this video is about projection onto a vector. So if you have two vectors, u and v, so if u and v are vectors in Rn, with v not equal to the zero vector, then it turns out that it is possible to write u as a sum of two vectors say w1 and w2, where w1 is a scalar multiple of v, so where w1 is parallel to v, and w2 is orthogonal to v. And maybe I should emphasize that when I say it's parallel to v, I mean is a scalar multiple of v. So w1 could be the zero vector. Okay, so this is a fact. And let's draw a picture to illustrate what's going on. So let's say that you have R2. So here's R2. And let's say that u is, say, this vector, and v is, I don't know, like that vector. So what's going on is, if you look at this line that is spanned by v, there is a scalar multiple of v, and it's going to be, I mean, what you can do is you can take u and then drop a perpendicular onto this line. So you have this 90-degree angle, and then you have this scalar multiple of v, like this. So this would be our w1, such that when you do u minus w1, so this other vector is w2, w1 is parallel to v, and w2 is orthogonal to v, right? So this expresses, in this picture, we've expressed u as w1 plus w2, with w1 parallel to v and w2 orthogonal to v. Let's draw another picture. So this happens in Rn, right? So let's do R3. So if you have this vector u, say it's, I don't know, here, and then let's say v is, maybe make it a bit different. I don't know. Let's say that's v. Then what would w1 and w2 look like? Well, the span of v is this line, and if you drop a perpendicular from this vector u onto this line, then you're going to get this 90-degree angle here, and then v1 is going to look like, w1 is going to look like this vector. That's going to be w1, and then w2 is going to be that vector. So so that W1 plus W2 is equal to U. Okay. So the question now is, well, from the pictures in R2 and R3, it's very plausible that this is true, that this fact is true, but how do we prove it for Rn? Well, what we can do is we can actually find what W1 and W2 are going to be. So let's see how we can find W1 and W2. So how to find W1 and W2? Well, once we find W1, then W2 is just going to be U minus W1, right? And that way, U will equal W1 plus W2. And what do we need to have happen with W1 and W2? We need W1 to be a scalar multiple of V. So W1 is going to be some scalar multiple of V. And W2 is going to be U minus W1. So that's U minus CV. And what we need is, what we also need is that W2 is perpendicular to V. Right? And so the question is, what is C? Because if we know what C is, then we can find W1. What is the C that will make W2 perpendicular to V? Well, when you think of two vectors being perpendicular or orthogonal, we think of what? We think of the dot product being 0, right? So we need the dot product of W2 and V is equal to 0. Well, W2 is U minus CV. And if that's orthogonal to V, that means the dot product with V has to be 0. And what does that tell you? Well, we can use the dot product properties that you can distribute the dot product. So this is going to tell you that U dot V minus C times V dot V is equal to 0. And just a reminder that, okay, what's going on here, because there's a bunch of symbols going on, U dot V is a number, okay, C is a number, and V dot V is a number. And this number U dot V minus this product is, it turns out it needs to be 0. And we're trying to solve for C, and can we solve for C here? Well, yes, because we can just add, right? It's just algebra at this point. We just add C times V dot V to both sides, and we get that U dot V is equal to C times V dot V. Now, the only thing we need to check, see, what we want to do is we want to divide both sides by V dot V, and then we get C. But we have to be careful, and we need to make sure that V dot V is not equal to 0. Well, can V dot V be equal to 0? Well, no, because V is not a 0 vector. And if you have a vector that's not the 0 vector, the dot product with itself will not be 0. Do we see why? Because if, let's just do a little scratch work. If you have some vector V with components V1 through Vn, then V dot V is equal to V1 squared plus dot 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 plus Vn squared. And the only way, if you have a sum of squares, if that's equal to 0, that's only if V1 is 0, V2 is 0, all the way to Vn is 0. And that's when, so i.e. V is the 0 vector. Right? And so since V is not the 0 vector, V dot V is going to be some positive number. And so we can divide both sides by V dot V because it's non-zero. And so we get that C is equal to U dot V over V dot V. And that's the formula. So in other words, we have, so W1 is going to be U dot V over V dot V, V. And I just want to remind you that this is a scalar, right? U dot V, the dot product of two vectors, is a scalar. So U dot V is a scalar. V dot V is a scalar. When you divide a scalar by a scalar, you get a scalar. So this whole thing is a scalar, and it's a scalar multiple of V. And W2 is, well, it's just U minus W1. So this vector is often called the projection of U onto V. Okay. So that's the notation. So let's just put a box around it. That's called the projection of U onto V. It's kind of a misleading phrase, U onto V, because you're not taking U to V, right? That's not what's, it's not like you're taking U and then somehow making it land on V or something like that. What's going on is this picture. You have V, and what's really going on is you have this line along V, and your W1 is a vector on this. Your W1 is a vector on this line, and W2 is perpendicular to the line. So actually, it's probably better to call it, so, or the projection of U onto the line through V, or the line spanned by V. And the projection of U onto the line spanned by V, that's what this is. We found the formula for it, but we actually have a notion of the projection of a vector onto a subspace, a general subspace. The line spanned by V is a one-dimensional subspace, right? But it turns out that if you have like a bunch of vectors, instead of just one V, you have V1 through Vk, that will span some subspace of Rn, and it makes sense to talk about the projection of U onto that subspace. So what we're talking about today is the special case when that subspace is a line through the origin. I mean, all the subspaces go through the origin. And yeah. So this stuff about the projection of a vector onto another vector, that usually is brought up in previous math classes. So it's often brought up in multivariable calculus, the chapter on vectors when they introduce the dot product. And it's even discussed in some pre-calculus books. And it's an important concept, projecting a vector onto another vector. This concept is used in physics. It has to do with, work and stuff like this. Sometimes you just want to decompose, like if this vector U is like a force or something, then W1 would be the component of U along the line, along the V direction. So that's one way that this concept shows up. And yeah, it's an important concept. And we talked about projection of a vector onto another vector. And in another video, we'll talk about projections of a vector onto a subspace. But the formula for that is related to the projection of a vector onto a line. So it's important to understand this first. Okay, thanks for watching. Well, yeah, do I want to give another example? Okay, let's do an example with actual numbers before we end this. So Let's do an example. So express the vector u equals 2, 1, negative 3 as the sum of a vector parallel to v equals 3, negative 1, 0, and a vector orthogonal to v. Well, that's easy. We just use the formula, right? So we have W1. So the answer is U equals W1 plus W2, where W1 is, well, it's the projection of U onto V, and the formula is U dot V over V dot V V. So U is equal to W1 plus W2, where W1 is that, and W2 is just U minus W1. Well, let's calculate W1. So we're given U and V, and so the dot product, so W1 is, I'm not going to rewrite it. U dot V is equal to, let's see, 6 minus 1 plus 0 is 5. So you're going to get 5 over V dot V, which is 9 plus 1 is 10. So it's that scalar multiple of V. So 3, negative 1, 0. And so this is going to be 1/2 of 3. So that's 3 halves, negative 1/2, 0. That's what W1 is. And so W2 is going to be U, that's 2, 1, negative 3, minus W1, 3 halves, negative 1/2, 0. And this is equal to 1/2, 3 halves, negative 3. And so U is going to equal W1, that's 3 halves, negative 1/2, 0, plus 1/2, 3 halves, negative 3. Should we just double check? We can see that these two vectors are orthogonal, right? The dot product is 0, which is what should happen. And is, when you add these two vectors, do you get U? Let me just make this a bit neater. Let's see, the sum is 2, 1, negative 3. Yes, that's correct. So that's the answer. Okay, I'm not going to draw a picture of this, but the picture is going to look, it's going to look like this picture here. Something like that. Okay, so that's projection of a vector onto another vector. Thanks for watching.